Hello, my name is Jack Kotovsky. I'm a mechanical engineer at Lawrence Livermore National Laboratory, and I'm here to describe a sensor from Nukes to knees, a contact stress sensor that is a sensor designed to measure interface load stresses, or contact stress between two contacting surfaces. I say from Nukes to knees as it was developed as a weapon diagnostic and is in production within the Department of Energy's fabrication facility and is now available for knee and other applications. There are a multitude of examples of interfaces where measuring the load or contact stress between two surfaces is important. Knees, helmets, robotic systems. There are plenty of examples where measuring the pinch forces between two surfaces is important. For example, in a running shoe, understanding the interaction of the sole and the heel at heel strike is critical to avoiding injury and developing better shoes or monitoring the aging or wearing of shoes. In a football player, understanding loads to the brain that cause concussions is critical to helmet design and preventing injury. In our soldiers, understanding blast overpressure and how it's devastating a multitude of soldiers coming back from abroad. There's a variety of examples where knowing interface loads either dynamically or in a research lab in the development of a product is critical. There are commercial sensors currently available, but there's a measurement gap for measuring contact stress sensing accurately and repeatedly, especially in an embedded application. Fuji pre-sensor film does a brilliant job of measuring interface loads, but is a pressure photograph and only takes one snapshot and can't be reused. The TechScan sensor does make repeated measures, but is only relevant to laboratory use as it loses its calibration after a small number of load cycles, as has been repeatedly demonstrated in the literature. Our sensor, on the other hand, is designed to be very thin and accurately measure interface loads across decades. We embed them in our systems for decades of use, and we count on them maintaining their calibration. We also are able to make dynamic measurements over 200 kilohertz in speed, as the materials that it's made from are very fast acting. The technology is built from a silicon sensor, much like a conventional pressure sensor, with the exception that these sensors are paper thin. Shown on a dime in a couple form factors that we currently produce them in, the sensor is disappearingly thin, but includes the circuitry of a conventional pressure sensor. It includes a Wheatstone bridge that produces a voltage output proportional to load and will do so repeatedly over indefinite use, as the silicon mechanically and electrically is very stable. The package that it sits in is also very thin, shown next to the edge of a dime there or in plan view on top of a dime. The sensor package is very thin to bring signal from the chip without producing added thickness that perturbs the measurement we're trying to make. Any sensor that's introduced at a load interface will change the measurement we're looking to make, so the thinner the sensor is, the better it's able to measure the contact stress. Shown below is a typical sensor output. That's voltage proportional to load, where we see a nice linear response, and we can adjust the dimensions of the diaphragm, both thickness and diameter, to give a very large range of sensing capability from several psi into thousands of psi, depending on the application. There's also interest at times in measuring load distribution. Instead of just capturing load at a single point, we might want to map load across a load interface. In that case, you need a two-dimensional array of sensors, and shown here are various prototyped arrays ranging from a solid chip, which is relevant to a flat surface, or a flexible, stretchable mesh of chips that are able to conform to arbitrary curvatures, like in the hip or the knee or around the head and underneath the helmet. An example of a 900 sensor array is shown wrapped around a pencil to demonstrate its flexibility. These sensors are very small, stretchable, and flexible for any arbitrary curvature. On the right are 200 micron diameter individual chips interconnected by spring-like electrical connects that allow that flexibility. As an example of embedded applications and a variety of dynamic and manufacturing applications, shown are some examples. For example, an automotive tire molding capability where understanding the load between the tire as it's vulcanized and the mold that it sits in is critical to real-time adjustment of the pressure, which will affect the yield and throughput of that product as it's manufactured. Another example, in development of a bulletproof vest or a soldier's helmet, capturing load between the helmet and the individual, or between the chest wall and a bulletproof vest during a highly dynamic event, is something that this contact stress sensor can uniquely provide. Currently, the sensor is in production within the Department of Energy for our internal programs and will continue to see expanded use, but is now available for external commercialization and fabrication. We look forward to it finding a home in a variety of research labs and ultimately embedded in products. For additional information, please contact our Industrial Partnerships Office, Charity Follett, and thank you very much for your interest in the technology.